I am A. Tausif Ahmad, leading to PhD degree course under the guidance of Dr. U. Rizwan, Associate Professor and Head, PG and Research Department of Mathematics, Islamia College, Autonomous, Vanyambadi. My paper title is Testing Bivariate Renewal New Better Than Used Aging Class of Lifetime Distribution Based on Moment Inequality. Abstract. In this paper, a new moment inequality is derived for bivariate renewal new better than used aging class of lifetime distribution. This inequality demonstrates that if the mean life is finite, then all higher order moment exist. Based on the moment inequality, a new testing procedure for testing bivariate exponentiality against bivariate renewal new better than used aging class of lifetime distribution is introduced. The asymptotic normality of the test statistic and its consistency are studied. Using Monte Carlo method, critical value of the proposed test statistic are calculated for n ranging from 5 to 100 with the interval 5 and tabulated. Finally, the theoretical results are applied to analyze the real life data set. Introduction. Certain classes of lifetime distribution and their variation have been introduced in reliability theory. The application of these classes of lifetime distribution can be seen in engineering, biological science, maintenance and biometric. The main aim of constructing new tests is to gain higher efficiency. Bivariate aging class of lifetime distribution is a new branch of reliability which is established by developing the measurement of success or failure concerning reliability. Bivariate distribution are observed in different practical situations. For example, in the survival of the paired organ such as a person's eyes, air, kidney, lungs, or in the survival of two-engine aeroplane in which the bivariate distribution can be observed. Next, testing bivariate exponentiality against some bivariate aging class of lifetime distribution has been seen a good deal of attention. The moment inequality for bivariate renewal new better than used aging class of lifetime distribution can be found in the work of Satyaraj and Rizwan 2019. Now we propose a test statistic for testing bivariate exponentiality against bivariate renewal new better than used aging class of lifetime distribution based on moment inequality. Next definition. Let x comma y denotes the survival time of a device having a distribution function f of x comma y. The bivariate joint survival function is given by f bar of x comma y, that is survival function of x comma y is equal to p of x greater than x, y greater than y, x for all x comma y is greater than or equal to 0, where it is assumed that survival function of 0 comma 0 is equal to 1. The following definition of bivariate aging class of lifetime distribution appeared in Satyaraj and Rizwan 2019. Definition. A bivariate random variable x comma y or its distribution f bar of x comma y is said to have bivariate renewal new better than used aging class if w bar of x plus t comma y plus s is less than or equal to w bar of x comma y w bar of t comma s for all x comma y t comma s greater than or equal to 0, where w bar of t comma s is equal to 1 over mu integral t to infinity integral s to infinity f bar of u comma v dv du. Here mu is equal to integral 0 to infinity f bar of x comma y dy dx denotes the finite mean of bivariate random variable x comma y, and it is assumed to be finite. Definition. The earth moment of a bivariate random variable x comma y is mu at r equal to expectation of x to the power r into y to the power r is equal to r square integral 0 to infinity x into xy to the power r minus 1 f bar of x comma y dy dx. Moment inequality. A moment inequality is derived for the system whose life time distribution is a bivariate renewal new better than used aging class of lifetime distribution. Then we prove this theorem. If f is bivariate renewal new better than used aging class of lifetime distribution, then moment of all order r for all integer r greater than or equal to 0 exist and are finite. Then mu at r plus t r plus 3 over r plus 2 into r plus 3 will less than or equal to 1 over mu summation I is equal to 1 I equal to 0 to r r c I 1 over r minus I plus 1 over I plus 1 into mu at r minus I plus 2 into mu at I plus 2 over r minus I plus 2 or into I plus 2. Proof. Since f is BRNBU aging class of lifetime distribution, we have w bar of x plus t comma y plus s is less than or equal to w bar of x comma y w bar of t comma s for all x comma y t comma s greater than or equal to 0, where w bar of t comma s is equal to 1 over mu integral t to infinity integral t s to infinity f bar of u comma v dv du. Multiplying both sides by x plus t to the power r into y plus s to the power r and integrating, we get the equation, we get the inequality 3.1. Considering the RHS left hand side of the inequality 3.1, we get mu at r plus 3 over mu into r plus 2 into r plus 3, where I is an indicator function. Further, we considering the right hand side of the inequality 3.1, we get 1 over mu square into summation I equal to 0 to r c I 1 over r minus I plus 1 into I plus 1 into mu at r minus I plus 2 over r minus I plus 2 into mu at I plus 2 over I plus 1. Using the equation 3.2 and 3.3, the inequality 3.1 becomes mu at r plus 3 over r plus 2 into r plus 3, which is less than or equal to 1 over mu summation I equal to 0 to r r c I 1 over r minus I plus 1 I plus into I plus 1 into mu at r minus I plus 2 into mu at I plus 2 over r minus I plus 2 into I plus 2. This completes the proof of the theorem. Further, testing bivariate exponentiality against bivariate renewal new better than used aging class of lifetime distribution. Using the above inequality, that is 3.4, we test the null hypothesis against the alternative hypothesis that H0 is f is bivariate exponential, and against the alternative hypothesis H1, that is f is belongs to bivariate renewal new better than used aging class but not bivariate exponential. Considering the bivariate exponential distribution introduced by Marshall and Alkin in 1967, given by f bar of x comma y is equal to exponential to the power of minus lambda 1 x minus lambda 2 y minus lambda 1 to maximum of x comma y. For all x comma y, lambda 1, lambda 2 greater than 0 and lambda 1, 2 greater than or equal to 0, we defined delta at E equal to summation I equal to 0 to r r c I mu at r minus I plus 2 into mu at I plus 2 over r minus I plus 1 r minus I plus 2 into I plus 1 into I plus 2 minus mu into mu at r plus 3 over r plus 2 into r plus 3, which is the equation number 4.1. Now note that under H0 delta at E equal to 0, while under H1 delta at E is greater than 0, let x1 comma x2 x3 comma x4 x at I minus 1 comma xi etc x at n minus 1 comma x at n be a bivariate random sample from a distribution f. Taking r equal to 1 in the equation number 4.1, we get delta at E equal to 1 over 6 mu at 2 into mu at 3 minus 1 over 12 mu at 1 into mu at 4. The estimate of delta at E cap of delta E can be obtained as delta at E cap equal to 1 over n square summation I equal to 1 to n summation j equal to 1 to n phi of xi comma xj, where phi of xi comma xj equal to 1 over 6 xi square into xj cube minus 1 over 2 xi into xj xj to the power 4. To make the test statistic scalar invariant, delta at e cap equal to delta at e cap over mu at r plus 4. Then delta at e cap is equivalent to the classical u statistic, and it is given by u at n equal to 1 over nc for summation I is less than or I less than j less than or equal to n phi of xi comma xj. The asymptotic normality of delta at e cap is summarized in the following theorem. As n tend to infinity, root n into delta at e cap minus delta at e is asymptotically normal with mean 0 and variance sigma square, where sigma square is equal to variance of 1 over 6 xi square mu at 3 minus 1 over 2 xi into mu at 4 plus 1 over 6 mu at 2 into xj cube minus 1 over 1 over 12 mu into xj to the power 4. Under H naught, the variance reduced to sigma square equal to 56. We prove this theorem. Corollary. Under H naught, the limiting distribution of u at n is normal with mean delta at e cap. The variance of root n un is a function of lambda 1, lambda 2 and lambda 1, 2. Proof. Since the variance of root n un is very complicated under H naught, and since un is a function of u statistic, the magnifying would not only reduce the bias but also enable us to estimate the variance of v of root n into u at n. The estimate of v of root n into un is equal to v cap of root n u at n equal to 1 over n minus 1 into summation I equal to 1 to n u at n comma I minus u at n star whole square. Using the result from Sen 1977, root n un over v cap of root n u at n whole to the power half is asymptotically standard normal, that is n of 0, 1. This completes the proof of the theorem. Monte Carlo simulation. In this section, the Monte Carlo simulation null distribution critical point of delta at e cap are simulated based on 50,000 generated at random sample of size n ranging from 5 to 100 with the interval 5. Table 1 gives the upper percentiles of the statistic delta at A for the different confidence level 90% and 95%, 98%, 99%. Critical value of the test statistics is given in the table 1. The relationship between the critical value, sample size and the confidence level. It is clear from table 1 and figure 1 that the critical value increases as the confidence level increases. Almost increases as the sample size increases. Application to real life data. Here we present a real life example to illustrate the use of our test delta at e cap. We consider the example given by Barlow and Prost in 1977, which is a list of paired first failure time in hours of the transmission and the transmission pump on 15 Caterpillar tractors. We use our test to detect whether this failure times follows a bivariate exponential distribution. Failure times of transmission pump X and the transmission pump Y on D9G-66A Caterpillar tractors. There are 15 parallel tractors X and Y and minimum of X, Y. Using the data in table 2, we obtained the value of the test statistic delta at E equal to 0.000151947. Thus root n into u at n over v cap of root n into u at n whole to the power half is equal to 8.263809664 into 10 to the power 9. Hence we reject H naught and conclude in the favor of bivariate renewal new better than used aging class. Then we accept H1, which shows that the data set has a bivariate renewal new better than used property but not bivariate exponential. Conclusion. The bivariate renewal new better than used aging class of lifetime distribution is considered the moment inequality is derived A new test statistic for testing bivariate exponentiality against bivariate renewal new but the new judging class of lifetime distribution based on moment inequality is proposed. Using Monte Carlo simulation method, critical values of the proposed test statistic are calculated for n ranging from 5 to 100 with interval 5 and tabulated. Finally, application to real life data is given. This all the references I have refers to prepare the paper. Thank you.